right. So. Well, welcome to the lab. This is week 9's lab, even though we're covering material that you guys covered in, I think, week 7. Today, only Mishka is here. Very nice. But we are going to do talk about constant error and variable error, which is used to measure how accurate someone is, especially in aiming tasks. So we're looking at lab 7.2, so you can download that online. And I guess to start off, I'm going to just kind of draw out what constant error and variable error mean. So let's say here's a target and people are trying to aim to hit the center mark, that X there. And let's just throw up a couple random places where they hit. All right. Do you know what the constant error of that would be? So constant error is important because it typically gives a direction. And variable error gives an average of the typical. But constant error giving a direction, you basically have to define what positive and negative means. So maybe here you would be like, okay, what's positive and what's negative, what's above the X and what's below. And so this constant error would be that distance from that target, but on the plus side. And here it would be a positive, whatever that distance is. And here it would be that distance. So whatever scale you have, maybe you get a 1, 2, 3, 4, 5, 6. Right? So this might be a +4. But so, and then down here might be a -4. And so if you have that, you know that the plus is anything above, and you know the minus is anything below. And it's just that magnitude that that distance was off. Now, variable error tries to give you an estimate of consistency, like how precise that person was. If you're throwing something at a target, how much error do you have when you're throwing it? So here, that would be, you take up all those distances, all those constant error distances, you get rid of the positive and negative, you don't think about it. You add all of those absolute distances, and you divide by the number of trials. So you get an average value. Basically, what it tells you is, so here you might get a 1 or 2 and a couple 4s and a 3 or 4. So you're probably going to have like an average of 3, maybe. You'd have an average variation. It pretty much tells you like a spread, how far apart it is, so how clustered it is. So if this is like a variable error of 3, a variable error of 2, you're going to have the spots clustered in much closer together. So the smaller the variable error, the closer they are together. But it doesn't necessarily mean that it's very close to the target. So you could have a very small variable error, like a 1, but maybe that person just kept hitting right up in the top corner. And that means you have a pretty high constant error, because that's going to be like a 5 on your scale, a +5. But your variable error is going to be really small, because that's all within like 1 point. So you can see kind of knowing both the direction And the clustering is important in knowing kind of how accurate somebody is. Now, I was going to have multiple people come up and try to do this, but if you see towards the bottom of page 2 on your lab, it tries to give just typical guideline of if you have a small constant error and a small variable error, it describes what it'd look like, clustered tightly and close to the target. So, Mishka, could you go draw that on there? Draw those 4 scenarios. So the first one's a small constant error and a small variable error. Yeah, so like all of the marks would be in that area. Okay, so the second one, small constant error and a large variable error. Yeah, it'd be like kind of all over. You're right in that it widens, but it necessarily doesn't have to be in one direction or the other. It's just going to like fill the area kind of equally positive and minus.
How's that a small constant error?
Because if you have a positive value and a negative value, they're gonna even out. So if you have +5 and -5, it'll be a constant error of 0. Okay, and then a large constant error and a small variable error.
So that'd be like a
Yeah, exactly. And then large and large. Yeah, pretty much. Nice. Perfect. All right, so that's like the basics of what this task is about. It talks about parking your car and how close you are to the center. But basically, constant error and variable error are important because they give you an idea of accuracy. And those values then allow you to compare between yourself. If you try a lot of different times, you can compare how you did on your first day of driving versus after you've driven for a year, or to other people. So it's a measure that then allows you to compare results between participants or over time. So getting into what the lab is about, so I guess you and I can do it pretty quickly. Basically, you want to make sure the video's on the right location. No. All right, this is the best. Okay. Basically, we're going to see how accurately you can redraw a length of a line and see what kind of constant error and variable error we can get. So, you have a pen? Would you mind coming over here? Maybe pull it around here. No, that's fine. Okay, so let's have you draw a line that's 14 centimeters at the top. So you see how long that line is? Okay. Now, what we're gonna wanna do is for you to redraw that line as accurately as possible without the ruler and without seeing the line. So I'm gonna cover it up and you're gonna draw a line. And then once you finish that line, I'm gonna cover up both and have you do it again. And you're gonna do that 8 times. So we'll get 8 measurements of how closely you can draw a 14 centimeter line. You ready?
Yeah.
All right.
Oh, that's good. Yep.
Now don't use my edge.
Okay. Okay.
Okay. I forgot it's gonna go take up more room. One more, right? Is that 8?
I don't know.
I don't know either. Great. Now, we need to measure. And I would measure using this side and write if you're plus or minus.
By how much?
Yeah.
Oh, that one's like, hang on.
Look at that. Perfect. 0 error.
So it's minus 5 mil.
Yeah, 0.5. Yeah.
Is that right on or just
Plus
one?
0.1.
Plus 1?
That's fine. My guess. Because I'm harsh, I guess. Nice. And so then it would want you to fill this in to calculate your constant error. So basically what you did here, the minus 5, that's is that constant or variable error?
What's the constant?
Exactly, because it gives you a direction. You're saying, okay, I didn't hit the target by 0.5.
Yeah.
Here, it's your constant error, 0, minus 6. So if you look at this, just looking, what do you think? You're going to have a small or a large constant error overall?
Small.
Yeah, because they're going to kind of,
But 8 and 6, and it's like 2.
yeah, you're probably going to be a little bit negative because you were, 5, 10, 16, 18 negative and 11, 12 positive. So you're going to be slightly negative, but typically pretty low constant error. But then your variable error is going to be the average of that. That's going to really help you with your variable error being so low. So, gives you an idea of constant error variable. Do you want to see if I'm any good at this? Or
Yep.
yeah, all right. Probably going to be much better than me. All right, so can I borrow your pen? All right, so 14 centimeters. Oh, I didn't even do that, right? You didn't see that? All right, so that's 14 centimeters. Yep.
Okay, are you ready?
Yep.
I think that's 8.
All right, this is gonna be bad. All right. So what do you think? Ooh, minus 1.2. And that's centimeters. We're on a different scale. Not good. Okay. Minus 0.8. Notice how I do it in centimeters so it looks smaller.
Oh, yeah.
plus 0.1?
Yeah.
Minus 0.3 or 4? It's kind of half in between, so you're harsh too. Exactly, retaliation. Gotta round up, right? Okay. Oh, minus 1. This is bad. Minus 1. Should have been shooting for 13 centimeters. Oh, minus 1. Now that's good. That's pretty bad. So, yeah, Michigan definitely wins. So I am, like, if you look at the trials, 1, 2, 3, 4, 5, 6, 7 of the 8, I'm negative. So my constant score is going to be very negative. And then it's also quite large magnitudes, right? Yeah, it's pretty good. It's probably going to be like average minus 0.8. Yes. So I bow to champion Mishka at accuracy in drawing a line of a given length. Does that kind of help you get an idea of constant score versus variable error? That's constant score, it's a different thing. Constant error, variable error. All right, so the main part of this is I want to talk more about data analysis, also kind of go over, there was the lab 5.2, that's a speed accuracy trade-off that we skipped last time you were here. And just talk in general about how I approach data analysis and kind of topics on how to think about variables in general and also what you might look at and why some of it's important. So if you have any questions, please jump in. But I'm going to have to sit over there because it's all on the computer. I don't know if you can maybe just stay there. You might want to grab 5.2. Of course. Can you say what? Yes, definitely. So most of the time I'm going to just keep it zoomed in on my screen so people can see what's happening. All right. Basically, so I'm going to have this credit assignment. There's 10 questions on it. Basically, what it's going to have you do is go look at the data we've generated from assessment 1 and experiment 2, which is the speed accuracy trade-off. So you guys have all the raw information, all the raw data there. And it's just going to tries to touch on some of the points that I felt were not too strong across pretty much everyone, not quite every group, but most. Which was mainly in defining a good hypothesis, which then led into summarizing your results well, how to analyze the results, and then tying them back to the journal articles. Because a lot of people could find good, relevant journal articles, but they couldn't tie how the data and the experiment we performed matched that, and how the results of the experiment went along with it. So this assignment you see on the screen right now might change a little bit. I might edit it a little bit, but basically this would be due pretty much midnight of Monday of week 13, because I don't think anyone has much else to do in week 13. Thought I'd at least give you a weekend to do it if you are struggling. But it's also completely voluntary. Don't have to do it. Don't have to listen to me right now if you don't want to. I just feel it could help people bring a grade from maybe not passing to a decent pass or up to what they normally would think about that would be receiving. I think there Yeah. Okay. So to do this assignment, then you need to be able to get to your data. So the couple things you're going to want to do is go into assessments in your 210. Download your assessment 1 and laboratory guidelines. This one will just, you can go to experiment 2, so you can kind of refresh yourself if this wasn't your experiment on what was performed. Experiment 1, here's experiment 2, so speed accuracy trade-off. And it corresponds directly to the lab 5.2. So you probably also want to download lab 5.2 because it also describes some of the meaning quite well in the theory that's being discussed. Okay, so you want to do that. And then you also want to go into assessment 1 and download the raw data, SPE2 assessment 1 data V2, which I have here. Okay, so this experiment looked at, we had 11 people finish it with all their data. What it did is people would, let's see if we have, Lab 5.2 did it slightly differently, but in a very similar fashion. So I'm just going to show you. People used those dots and had to place a pin mark in each one as fast as they could. So going back and forth, and you counted how many times you did that in 10 seconds. If you missed more than 4 times, then you had to redo the trial. But there were different conditions. So the conditions were how big, if the dots got wider, and the spacing between the dots. And if you look into lab 5.2, it tells you that those two things, that movement amplitude, the distance between the dots, is what they call A in Fitt's law, and the W is the width of the target. And so there's a defined relationship between this ID, index of difficulty, and how fast people can move. And basically, this relationship has been shown so many times that it's been termed a law instead of just a theory because it's quite often shown. And so that's what we controlled. We did different index of difficulties. So we went back to the task. We changed that width between the target, the size of the target, as you can see here. So you can see all the different types. Now, in the experiment we ran for assessment 2, there were 8 different styles of these, there were 8 different conditions. But some of the conditions were so that the index of difficulty, I think for condition 5 here, is the same as condition 4, because this target is half the size of that target, and this distance is half the distance. And so there's a steady relationship between the two. And so sometimes you would have 2 different conditions, even though they're different size targets and different distances, they were supposed to be the same index of difficulty. So this is, what I've done here is I've taken kind of all the information that was given to me during the time, because you guys were given just basic data. Here, this was the sheet you were giving. You were given what the subject initials were, what gender they were, their age, and then, okay, you were given also what methods were used, so it kind of described the experiment. It was told that it was tied to lab 5.2, so you could see that it was tied to Fitt's law and the index of difficulty. You could find but then you were giving these summarized in this kind of basic form of how you would collect data. This is not necessarily helpful for analyzing data. So basically, from that information, you had to develop testable things. Like you needed to try to have you needed a results section, a discussion section, and conclusions. And all of those things depend on being able to form a very solid, testable hypothesis that is based off of evidence. And so to do that, to be able to look at the data and you see basic numbers, you have to then be able to be like, okay, what does this mean? What could I possibly look for? Hints are given in how the experiment was written. Hints are given in the tying to Lab 5.2, but also you can look through your textbook and find speed accuracy. I forgot what chapter it was, but it's in there. The next thing is like, okay, what kind of comparisons? Because you got to develop a hypothesis. Typically, you do background research. Okay, so here, first thing I would do is go to Google Scholar. So I just Googled Google Scholar, I click it, and basically the first thing I ever really do is put the most basic thing in, see what pops up. Here's a publication that has 905 citations. It's obviously going to be fairly old or older, and it's going to be so it's 77, but you can have the PDF. You can start looking at what people look at. If you have a specific topic that you're interested in, maybe recognition memory, you know, this was a good one, 307 citations. But you can see a lot of these are older because this is a very basic law. But then you got to think of, okay, what information do I have? I have only what index of difficulty it is. I have the number of hits for my 11 participants, and I have gender and age. So what kind of comparisons can I do? Well, one of the first things you could think about doing is, does this actually fit the law? There's a common law out there that says with the increase in index of difficulty, there will be a linear increase in the number of, or the time it takes to move between dots. So that's one thing you could test. That's a hypothesis because you do have the number of hits, they call it, and you have the amount of time. So you can determine how much time it took per movement. So you can see if that law fits. That's one of the basic things I would definitely do in the poster. Okay, does this still work? You have gender. You could be like, oh, does gender make a difference? So then you could even type in up here, gender differences. And adult age and the speed of accuracy trade-off. You have an exact match to that topic. And you could say, okay, is this, you could then be like, all right, well, we know gender. We can test this. We can actually see are women or men faster or more accurate or whichever it is. And you can then compare it to this. You go to the paper and you can look at their results and be like, do my results match that? And so it was concluded that although SPEEDNet cannot account for all age differences in speed, the greatest bias towards accuracy in older subjects. I always love when they say to future researchers, or future research necessary kind of thing. So I haven't read this one either. So there's more accurate in older subjects, but slower. Yeah, I would have to go into that to see actually if it's data. So that was age, that wasn't actually gender. So I lied a little bit at the beginning. But this is how you go through it. You're like, okay, does gender, does age? You can often then, if you go into the papers, they'll have actually the information on gender and age just kind of hidden inside. So you can go find pretty quickly some relevant articles. So let's say this one was extremely important. Again, if you want to cite it, you can pick your type and copy it and paste it, and you have it. You can also, often over here, you get PDFs. You can just have the entire PDF and go through it and see if it actually helps your understanding of the topic, which is most important, and then later, does it match or refute some of your findings? Maybe you find that index of difficulty didn't increase time, and you need to refute all these other papers. So that's basically how I go about kind of figuring out topics. I start with the basic one, and then I go into the questions that I have. And sometimes I just look at topics. What did people look at before? But okay, so that's kind of the background research part of it. But now you have your data, and you need to look at it in more detail. Mishka, what's one of the first things you do with your data? What do you try to... Sorry? I just couldn't hear anything.
Because isn't there like the results for every 3 trials? So you just find an average for the trial.
Okay, so you mentioned, yeah, there's 3 different trials, and so you want to try to summarize results maybe for a person in an average. Average and median, those are 2 of the most basic statistics that you can have out there that give you an idea of the middle point of where you typically landed kind of on the trial. So basically, yes, you need to get the information in a way that is useful to analyze. So right now, having it in this form isn't incredibly useful. You need to have information in a way that you can calculate averages. What else what's another basic stat that you might want to know? So you kind of the middle point. What's another one that you might want to know? Sorry? Best, yeah. So how close you are. And then what's the opposite of that? The best. And then you had your best performance or your worst performance. So that statistically would be called your range. So how close and how far, how much of the area does it cover? So maybe let's look here, trials in just for this round. You could calculate average, and then you could calculate. Then your range would be, your low is 15, and then the high is 62. So his best was 62, and his low was 15. That's quite a high range, but these are all different index of difficulties. So I probably actually did this in the wrong order, because this is the same one. The 38, 38, 36 would be what you want to compare. So I did that wrong. But yeah, but getting back to the actual point I'm talking about here is the basic statistics that you usually perform are what you call descriptive statistics. So you usually have either a median or an average to give you the kind of the midline, the where you normally hit. You get a range, like Mishka talked about, like the best and the worst, And then you also get one other thing, it's the variance. So like what we just talked about earlier, the variable error. So it's kind of the average difference between the recordings. So do you know what I mean by that? So here is 38, 38, and 36. That's for the same index of difficulty. First time they got 38, 38, 36. So how close together is that? So the 38, basically they're measures of how far you are from that middle value. So sometimes they use the mean, sometimes they use the median, but it's, if you have like the target, it's how precise you are, how closely you reproduce that same value. So if this guy was good, he got 38, 38, 36, that is like no variance. But if you would look here, and if this was the same trial, if you go from 15 to 62, that's huge variance, and you're going to have a high standard deviation is a typical one. You can have a confidence interval. But these are the basic concepts and descriptive, and they call them descriptive statistics because if you just look at a sample, you'll be able to, by knowing what the average get, how much variance there is in the measuring, which is like the standard deviation or the confidence intervals, and then also knowing the range of the values you see, you get a good idea of what was measured. You can see how far apart they are. You can understand how reproducible they were, and you can see what the approximate middle point is. So basically, what I do when I get here, and you can always organize data differently, but typically it's best, so I have a spreadsheet here where I started to organize it differently. It's typically best to have, for one row, it'd be one participant. So I also, sometimes you don't want to actually give initials because that gives out identifying information about the person. So you might want to replace participant initials with participant number. So 111. So you give them numbers, you attach, you write down their information, you put their age down, and gender. So then this information, so this is HITS trial 1. So I go up here, and it's this column right here. So you see here's the ID, 1, 2A, 2B. You can see that that's here. That's the number of hits. The reason I have a couple different lines here is because here I actually wanted to plot the information later, so it doesn't actually make a difference. So here are the actual IDs. To get that information there easily, you can copy and paste it. So if you right-click, copy, you can go down here and right-click, but since it's in the other direction, you have to hit this transpose. So you get the information down there. And you go and you do this for every person for HITS trial 1, then you got misses, you got trial 2, hits and misses, hits and misses, right? So it's quite a bit of information if you scroll across. So then you go to HITS trial 2, HITS trial 3. I often use colors to distinguish between different things. It makes it easy. And so I get all the information for each participant in there. Now, if you notice here, I've actually only done it for the first 9 participants because this is going to be your assignment to go back in and fill this out for all 11 people. And so then the numbers I show you here aren't going to be the exact same as what the answers will be for the thing. So you have to go in and do this if you want to. But I hope it'll help you understand kind of data analysis and what you might want to do. So basically, so we got number of hits, but that doesn't actually correspond to Fitts' law. Fitt's law talks about this movement time, this MT. And in the instructions of what was done, it tells you how to calculate it. And to calculate it, you do 1 divided by, and you do the median of that trial. So if you go back here, I don't know if you can see it, but there's the blue square. That's the value 1. So that's ID 1. That's what they did the first trial. And then you see here the green one. That's trial 2 and trial 3. And so that here, and then you divide by 10. That is a formula that is on your sheet. So once you get that value in, let's say you don't have the rest of these, you can actually hit this little corner over here and drag it over, and it'll fill it in for 2. And you can go check it and make sure it does it right. So so that's an ID 2, and it's trial 1, trial 2, right here, and trial 3. So you can easily fill in the calculations for determining your median movement time. Now, another way you can do it instead of median, you could use average. Now, they give you approximately the same thing. It's a similar formula. So I actually think I only asked for median in the worksheet, but basically it's the same formula, but instead of median, you have average. Mishka, do you know the difference between median and average? Yeah, it's a very small difference, but let's just go up here. So median would be if you would go in and then order all these numbers from smallest to largest, and because there's 11 of them, you want to pick the middle value, which would be the 6th value. That middle value is going to be your median. And so let me actually, I'll do that. So you can go up here and you can go sort smallest to largest. It didn't really do it, did it? What's happening here? So here, I then sorted it smallest to largest. You can go down to the 6, 1, 2, 3, 4, 5. Oh no, the 5th one. That's not 11 trials, that's 8. So what do you do if there's 8? You then take, if there's an even number, you take the 2 middle values there, and you take the average of those 2. So that one would be 27. Now, average just adds up all the values and divides by the number of values that are there. So that's the difference between median and mean. And people will go into lots of depth and argue a lot about, okay, which one's the best for different methods, but definitely don't worry about that here. We focused on median, so that's this value here. So you calculate the median for each trial, for each index of difficulty. You can get it plotted. And once you calculate it across, you can also just drag it down and it'll fill it in. So I'm going to just, let's say I didn't have this information. You can just go in and fill it out by doing that. After you get the first value right, just make sure it's calculating the right things. Excel's pretty good at these kind of things. So now what you wind up with is you have your median times, you have your index of difficulty. Now, if you're trying to show that your your movement time and your index of difficulty are related, how might you try to visualize that? Would you? Sorry? If you're trying to show whether or not your movement time goes up with the the index of difficulty, how might you try to visualize that? In like a form, like to see something, how would you try to do it? Yeah, so you can kind of look at the numbers and see if they follow that trend, but better is plotting it. So here looks at your index of difficulty and all of the data points for every person, which is kind of cluttered, right? So you see this graph here, you got index of difficulty on the side, and you got your movement time on the y-axis. Now, there's also, typically on the y-axis, you always put the variable you're trying, that you measured during the experiment on the y-axis. And you put the experiment variable that you tried to control on the x-axis, typically. Sometimes you'll have, on different graphs, like 2 measured variables, 1 on each side. But if you're trying to show a comparison, you always put the one you measured on the y, and on the x-axis, you put the one you controlled. And so we had different index of difficulty conditions, so we put this on the y, or the x-axis. So this is cluttered. You can clean it up often by putting in averages. So here you can see is a zoomed in version, and these points here, let's zoom out again and go over. If you go here, this is the average, and it's plotted against the y. So I'll actually show you how to make one real quick. Let's see if I can remember how to. So we're going to insert, and you hit scatter. Not quite right. So it didn't. So let's try again. Insert, scatter. But it gives you in the there we go. So it was flipping which axis was y and which axis was left. And now you can see that it has all of the data just there. And so you can also, from your numbers, 1, 2, 3, 4, 5, up here, you got the index of difficulty and your movement time. Now, when you look at this, would you say that this follows Fitts' law? How can you tell, like, if your hypothesis is that your information, that you're going to increase your movement time with an increase in index of difficulty, how can you say it definitely? What do you need to have experimentally talking? You need to have statistics to back it up. So one good way to do that is to see if there's a linear relationship. Basically here, if you go in, let me try to recreate this graph right here for you. So we're going to want insert scatter. We want to know, we want index of difficulty, and we want the average. You got to hold down Control to get two different rows. And you go insert, and you go scatter. And this kind of makes sense. So if you look here, you got the index of difficulty down here, because you know you got numbers 1 through 5, and it only has points on 1 through 5. And you also know that you have two index of difficulties at level 2 and 2 at level 3. And you can see that here, and 2 at level 4. Now, to see if it goes up and do a linear regression in Excel, you can right-click the points and say Add Trend Line. Here, to see information about it, you can say Display Equation on Chart and Display R-squared value on chart. And you get this information. This information is important. It tells you what that relationship, it defines the mathematical equation behind this line. It tells you that with every one increase in y, you're going to have a 0.0786 increase in x. And this here, over here, that's called the offset. That's like if you would extend this line all the way down, it's where it crosses the y. So this completely defines the equation of that line. You can take it out to indexes of difficulty 7 or 8, and if you have a true linear relationship, it would continue in that way. Now, this R-squared value is a very statistically often used term. Basically, what the R does is it explains the amount of variance. It's kind of technical with how it's done, but it's calculated based on something they call the sums of squares of differences. I'm going to try not to go into too much detail, but I want to kind of explain where it comes from. It's how far, basically that's how far these data points are away from that line, and then they add all of that up for each individual point, and they square them so there's no difference in positive and negative, and then they take the square root, and you wind up with this number that you also then square. It's kind of a convoluted way to say it, but the important thing is to be able to interpret what that means. If that's close to 1, the closer it is to 1, the better that line fits those data points. And so if it's, and there's general rules out there for what it means to have a good R-squared. Typically, if it's greater than 0.8, it's a very good explanation of the data. And if it's greater than 0.5, typically it's a decent, it's like okay. They consider it okay. And then below that, I think there's another level at 0.3 that they're kind of acceptable, but then after that you're going to have, like, there's not really a linear relationship. Don't try to say that something increases with the other. So now that you kind of, so this R-squared, it explains the variance, and what you can see here is that this index of difficulty does very significantly go up with the median movement time. That's important because the reason you can say that is because of how high this R-squared value is. Because it's 0.96 here, you know that as the difficulty went up, so did your movement time. Does that make sense to you, Mishka? Now, if this R-square value would be really low, let's say, if you had points like up in the corners here and all over here, you would have a line that kind of went through it, and you'd have it wouldn't make sense. But here, this can tell you statistically that yes, it does follow Fitts law. Wait. So the other thing that often people didn't do that's important is these values, these little points here, are summarizing, in this case for mine, it's only 9 different people, but for your case, it'll be 11 different people. So it's not a singular point. If you only have a dot like that, people think it's only one value. So you need to put in error bars. So this gives you it'll gives people more information on what you do. So to do that, you go into this chart tools section to lay out error bars, more error bar options, custom. It's very difficult to get to in Excel, but then you specify value, then you have to go choose it. Now I'm covering it, so I gotta exit. So here, I gotta undo. All right, so here is my average of the medians, all right? So I calculated the average of all the values I had here. And here, I did the standard deviation, and here it's .p, so it gets rid of logicals. You know, really, that's less important. But then I still do the same values, and so that standard deviation gives you how much the average deviation from the mean is. So if your mean is 0.24 and your standard deviation is 0.5, it means that typically the response is going to be between 0.24 plus 0.05 or minus 0.05. So between 0.19 and 0.29. You're typically, these responses were between 0.19 and 0.29. And if you look here, yeah, that's pretty true. There's a couple outside, but in general, this gives you how much variance. And if you look here, that variance increased between the index of difficulty of 1 and 2. So to get these values on the chart, I needed to be able to see them because Microsoft Excel makes you click a lot. So I'm going to go back and try to add error bars again. So I go layout, error bars, more error bar options, custom, specify value, and select the standard deviation. And negative is the same thing because standard deviation is how much plus and then how much minus it is. So you say okay, and you go back, and for some reason they're putting it on both the x and y axes, and this is only in the y, so I get rid of the x. And you can see here, now you have the error bars of how much variance. What you can see here then is for index of difficulty 1, look how small those error bars are in comparison to 5. Then you know there was more variance in response for the harder ones that were further apart and smaller. Okay, so that would be testing a basic hypothesis. Does our data match the match fits law? So and for it to be a good hypothesis, there's 2 parts it has to have. It has to be based off of evidence, and it has to be based off of, and it has to be measurable. So you have to be able to test it. So I would have to make that hypothesis more specific. I would have to then say, because what I said doesn't fits law. Well, what do you mean by that? You would have to say, does median movement time increase with increasing index of difficulty? That is then testable. You gave a direction and you gave the variables you want to talk about. Okay, so one question I ask you in there is about identifying variables, and I kind of skipped that at the beginning. And so I need to go back over that real quick. So the variables you have when you're looking here, you have hits, you have misses, you have initials, you have gender, subject age, And then you can calculate things based off of this information you have, and you have index of difficulty and these distance and width. So if you're looking at this, there's different types of variables. There's what they call independent variables. And the names of these aren't so important, but the concepts behind them are. Independent variables are variables that you controlled in your experiment. So they are kind of the groupings that you had, the experimental groupings. So here, Mishka, could you recognize maybe what the thing you controlled here? What did we change? What did you manipulate in this experiment?
Squares and the gaps between the size of them.
Sorry?
The width of the squares and the distance between them.
Exactly. So width and distance, and that's the index of difficulty. So here, this ID is going to be these are your controlled variables, are independent variables. Now, what are the things we measured? We measured hits and misses. Those are what they call dependent variables because they depended on the groups you were in. And those are what you have a value you measure. You can also usually take these and calculate different things, which is what we did because we took that number of hits and we calculated the movement time it took for each hit. And so instead of just having 38 hits, we had 0.2 seconds that it took to move back and forth. So we changed this hits into a different variable called movement time. Then those are the basic variables you test. Now there's something called grouping variables, or these are variables that describe your participants or whether or not you have different subjects or anything. So here we have gender because you got male or female. We have subject age, which is 20. If you were collecting information on running or something, you might have how many years experience they've been running, or an athletics team. These kind of variables, they often call grouping variables, that you can then separate your information into these different groups. They're not typically the main subject of your study, but they can be, but they're other variables. So here you would have an independent variable of the index of difficulty, dependent variable of the maybe movement time or hits or misses, and you would have the subject details be your grouping variables. Okay, so now we've talked about here. I kind of showed you how to calculate these values. You can, at the bottom, do the basic descriptive statistics. You can do like averages. Then you can do standard deviation, which I showed. But you can also then do like min and max. So then you know that, okay, to describe this completely, the index of difficulty 1, I would say in my results that they had an average of 0.24 movement time plus or minus 0.05, because that's your standard deviation, with a range of 0.16 to 0.32. And then if you're going to be extraordinarily specific, you say then n equals 9, because I only had 9 participants, but you actually have 11. So you would put n equals 11, because there's 11 participants. And those are the descriptive statistics that are the very basic way of describing any form of data. You have an average or median, you have a variance, and then you have how far they spread, the range. I'm guessing this is going to get quite boring right now, but then the next thing you do is, here we just talked about that. So basically, I had that massively long tables, right? We really, when we're looking at final stats, you want to pick out one thing and try to test different hypotheses. I showed you just recently how to add the trend line to see, does it actually have a linear relation? Does one increase with the other? Now, can you think of, Mishka, just if you can't, don't worry. Can you think of any other things you might ask yourself based off of those variables we collected in kind of, because you also read some of the literature on this topic. I know it was a while ago, but what other things might you be able to test to see, like, did this happen? Yeah. Or what? Exactly. So you can break up the data a bit more and group it. And so one of the early, I think, pitfalls that some people ran into is they didn't write down clear hypotheses. They didn't say, did median time, or we expect median movement time to increase or to decrease, or to increase with age. You didn't write down anything that was based on evidence, like you didn't see that that was reported earlier, or you didn't expect that because you know your movements get slower or whatever when you age, and you didn't make it measurable by saying, okay, here's the variable, I'm measuring it because it shows, and give a good reason. It didn't flow into that. As soon as you have a good hypothesis, it's much easier to test it. And to test things, and why I'm talking a lot about statistics, is because if you just look at the data, you just see these numbers, you can't really say for certain, okay, is level 1 different from level 2, and level 3 different from level 4. You want a way to mathematically be able to say that, a very unbiased way of being able to show differences. And that's what you do with statistics. And so again, basic is descriptive. And so equals average, and then you select your information, equals standard deviation. And you select your data, and then min and max, which I showed you before, and then just drag those across, and that'll show you your information. Now, one of the questions I came up with, I'll get to the gender and things later, is are there any significant differences in the median movement times between the index of difficulty levels? So what I mean, like, is there a difference between 1 and 2, 1 and 2A, 1 and 2B, 1 and 3A, 1 and 3B? And to do these, typically you can use what they call an ANOVA, a t-test, I think there's f-test, there's lots of different ones. Excel has t-test available, so we're going to use that. And so basically, I'll just, to do the t-test, right, I'm going to just, I'll show you how. So you go equals, Jim does it this way. So you can go up and click this little function symbol, the fx, and then you type in t-test. Go. And you want the t.test. It's the newer version for some reason. All right, so you hit OK. Basically, I want to know, right here I say, okay, it's ID1 versus ID2A. So I need to select the data. So array 1 is the data for index 1. That's going to be all these people up here. All right, and so then you need array 2, the data for the second group. So that first group is index of difficulty 1, array 2 is the second group of 2A. All right, so these are the the data you're trying to compare. Now, statistics always have funny, different things that they need you to specify in order for the math behind it to function. And it'll function differently for the values you put in. So it's very important. Here is called tails. And tails is quite funny, but if you think of it, tails is like, so if you have data and you think whether or not it's going to increase, that's one direction, or if it might decrease, that's another direction. And they're called tails here. So if you have one tail, you're assuming that it's going to go in one direction. Whereas if you say it's two tails, it means it could either be positive or negative difference. Almost 95% of the time, you will put two there, right? Because you don't know whether or not it's going to increase or decrease. However, on this particular example, you're testing whether or not it fits Fitts' law, which Fitts' law says that as you increase movement time, you're going to increase, or as you increase index of difficulty, you're going to increase the movement time. That's showing you're going to increase it. You're not going to increase or decrease. So that's a one tail. So for this particular example, it's okay to use one. Typically, people are safe and put in two, and even some journals will only allow you to submit two-tailed tests because it's harder to get significance. But we're doing one here because that's the law. Now the last part is type. This is the kind of t-test, whether it's paired, two-sample equal variance, or two-sample unequal variance. These are all very specific things. But paired means that, okay, so if you look at your data here, you got index of difficulty of 1, and you go down the list, all those participants are the exact same as the participants in the column 2 variable. Because they're the same participants, that's called paired. And so for here, you would say it's paired. And you say, okay, and then it calculates it. What that returns is a p-value. Do you know what a p-value is? P-value is based off something they often call alpha, and they always say 0.05. If your p-value is less than that 0.05, it's significant. But you can set this alpha to different values. You can make it lower, higher, but you always have to give explanation. But as long as you leave it at 0.05, you're usually good. This is so this means that there's a 5% chance that 0.05, if you get an alpha equals 0, that's the level of. But your p-value, if you get a p-value of 0.05, you have a 5% chance that result would have happened by chance, that difference would have happened by chance. If you have an alpha of 0.07, it means there would be a 7% chance that it could happen. So the smaller that alpha is set to, the more unlikely it is to happen by chance. So here, the p-value that results of 0.21 pretty much means that there's a 21% chance that those differences you see there happen by chance, and you would say that's non-significant. And really, according to this test, there's no difference between ID level 1 and 2. Now, 1 and 2A, I did it for also 1 and 2B. So I used, there's level 1, level 2, and then I did a one-tailed with, and the type of, which is 1, which was the paired test, right? So to fully describe, okay, so then I compared ID level 1 versus 3. You can see 0.0006 is your p-value. Mishka, is that significant? What does that mean? Yeah, 0.0. There's a lot of 0.0s there, so it's like 0.06% of a chance that it's going to happen by chance. But then if you look at 1 versus 3, right? If you look at these two rows, you can then, if you go back and look, you can see that ID3 is higher on average than ID1. So you could go and actually say ID level of 3 is requires significantly more movement time than ID level of 1. And then if you go from 3A to 3B to 4A to 4, like you can see all of those are significant. And so you know, going from levels 1 to 3, 4, or 5, all significantly harder. It takes more time. Now, another question I thought of that could be interesting is they didn't just do one level index of difficulty at level 2. You did 2. So you kept them the same. Like if I would go back to here, because like condition 5 and condition 4, they're actually at the same index of difficulty level, but yet they're two different things. Like this is half the size and half the distance. They're the same. Does that make a difference actually in our data? So the question I wrote down was, are there any significant differences in median movement time? Does the median tap time stay the same for the same index of difficulty, even when the box width and distance between the boxes changes? So is 2A different from 2B? Is 3A different from 3B? Is 4A different from 4B? So did that relationship actually stay true? That's also testing Fitts' law. And then you can go here and go back and do the t-test again. So again, you go and you select your 2A, which would be here. Then you go select your 2B, which is here. And you select your tails. I actually did this wrong. You'd want 2 tails here because you don't know if there would be a positive or negative difference. So you'd enter 2 tails. And it's also paired because it's all the same participants for both. And so you say, okay. And if you look here, you can see the p-value, 0.6 pretty much. So absolutely not significant. So there's no difference from 2A to 2B. Now, if you go look at 3A and 3B, you do very similar. So you select 3A and 3B. You select the right number of tails. And you select paired again. And you would do the same for 4. And you can see that there's no difference. But what you also notice, because I made that mistake, I'll show you. I'm going to undo what I last did. No, it's undoing my... look at the value. So this is the value of 2-tailed test. The p-value is 0.38. And a 1-tailed test is 0.19. So you can see that a 1-tailed test, you're more likely to get significant differences because you're assuming that it's going to happen in one direction. So that's why people don't usually like you to do it. They think you're cheating. But if you have it based off of a law, it's fine. Or a finding, if you have good rationale. Okay, so getting back to Mishka's point about what you can do about testing between, these would be like grouping variables, gender or age. Here is gender. So I looked at index of difficulty of 1 between gender. In order to do that, I've already done it on this one. But if we go back to my data previously, if I go all the way, here. Note that it's not in order of gender. So in order to be able to do this in Excel, you really need to have it in order, or you have to select the boxes individually. But one of the things I usually like to do is I sort it. And when I sorted the data, and you can see now that the participant numbers all flipped around. Here, let me show you how I've sorted it. So I'll go back to what it was. You can, this is how it was. So you have the data, and you have participant number 1, 2, 3, 4, 5, 6, 7, 8, 9. To sort this in a way I find meaningful for male versus female comparison, you highlight all the information you want sorted and highlight it all together, otherwise it won't sort it properly. And you can do what they call a custom sort. And basically, you enter which column you want to first sort it by. Since we're interested in gender, that's in column D. You say column D. It doesn't matter if it's A or Z. So then you can also do this thing called add a level. And maybe you want to then by age. So that's column C. So then you can see, okay, female age range from 20 to 21, and male's age range from 19 to 51. And again, this is only for my 9 samples, not the 11 that you have. But what you also see here is there's 3 females and 6 males. Statistically, that causes issues because you don't have equal sample sizes, and it makes it less likely you'll get statistically significant results. It also means that the variance and things will be very different. All of those things are very boring kind of statistical stuff, but do know anytime you see different numbers in groups, it makes it much harder to have very strong statistics. Okay, so going back to, are females or males better or worse than the other one? So you'd want to look at this median movement time. Which one, but what do you compare? Is it for easy values? Is it for the most difficult ones? Is it for, we didn't specify, we just said, oh, are females better than males? So then you would have to define which ones you want to look at. If you want to do an overall, but does an overall one make sense? I'm not sure. So what I would do is because we just went down here and we saw that there's no difference between 2A and 2B, and there's no difference between 3A and 3B, I would group it and I would look at if male and female are better for index of difficulty 1, for 2, but I would combine 2A and 2B. And for level 3, see if there's any difference in level 4. So I do it for each difficulty level. So that's what you can see I did here. So I'm going to click this and go up here and show you what I did. All right. So we wanted to see if gender made a difference between male and females for the reaction time. So I need to select the data for females. So you got females here. And then you want to, and this is index of difficulty 1, then you want males. So I select the male data. Now, tails, what would this be? Because you don't know if it's positive or negative, so it'd be 2. And now here's the type is quite interesting on this one, because if type is not, so 1 is if it's paired. So you have the same exact participants. That male and female, you don't have the same participants. So it can't be paired. So it has to be one or the other, the 2 or 3. And note that the numbers 1, 2, or 3 here don't actually mean anything. If you would report it, you'd have to actually say, oh, it's paired. Or the other ones are if there's a homogeneity of variance. So is the variance equal, or if the variance was unequal. I've actually gone and tested this for you guys. It's an assumption of the statistics, and all the variances were equal. I used a Levine's test. So don't do that, but know that you had to choose that there is some assumption behind there. There's tests to see if there's equal variances. And this test I did said that there were equal variances. So you can choose type 2, which is homogeneity of variance. And so, interesting. For that shows, let me go back. Yeah, that shows that there's a p-value of 0.045. What does that mean, Mishka? Significant. So you go up here and you see the girls versus the boys. Looks like the girls are a bit lower on index of difficulty of 1. So then you would go and do this for 2. And I've had before I tested whether... So here you can see 1 is paired, 2 is 2 sample equal variance, 3 is unequal variance. I've checked it's equal variance. So now index of difficulty 2, there's really no difference. 3, so you go up here. And notice how I selected them. Because 3A and 3B, there were no differences between it, I've grouped them together. And so comparing females to males for all of group 3, you can do it like that. And you don't see any differences. But then you go up to 4. And you get a significant difference again. And 5, again. Oh, that's wrong.
Question.
Yes.
Because pretty much all of them are between 19 and 22, I think, except for one, it's 57, the age difference. Would you take out that one to eliminate the possibility of that interfering with the male scores?
You could very well do that. That's a good point to do. There is a female in the 2 subjects I didn't do that's like 36 or something. And so that's why, like, normally I'd be like wanting to see, oh, is there an age difference? But most of the participants are between like 19 and 23, or, very close age difference that shouldn't matter, so that comparison doesn't make sense. But yeah, you're right, that 51-year-old might mess with all the stats. What I would do before I would exclude it is you can look for outliers. Is that person's results, usually it's like greater than 3 standard deviations from the mean, which if you look at that, it's not really. So you could leave it in. I would leave it in because he really kind of fits with the category. That's my statistical answer. But that is a very good point, because it's like that person is over double the age of the other. Does that make a difference? And should I have... But you can also, when you design the study, just say, I only want people between this age group. And you wouldn't have that. But we just tested people who were here. But exactly, if you could get rid of that, you could... And if you test it and you're like, I don't want that person in there, and you give a reason why, and you say that we did not include anyone older than the age of 24, and tested it, I would have had no problem with that. There's a reason why you did it, and you stated the rationale, and then you did your analysis. Perfectly good. It's a good point. So then, as we just talked about age, I plotted this, and you can see the person's age versus their overall median movement time. This plot is kind of interesting in the fact that you can see all the people grouped together in their age group, and then the 151-year-old over here. And looking at this, we saw earlier that median reaction time, movement time, actually went up with index of difficulty. What does this here say? Like, what would you say that this is important?
Is it saying that it's not going to have a linear?
Yes. Why? You're correct. It doesn't yeah, it's very close to zero. That means that 3% of variance is it's really low. There's actually a p-value you can get for a linear fit, but I don't know how to do that easily with Excel, so I'm not asking you to. But this R-squared, you can really see that this makes no sense to do a linear analysis here. You don't have enough data points. You don't have so this clearly shows age doesn't matter for this, but you also know, because you see the scattering of the data, it doesn't make sense to really do that analysis because you have all small and so you can do even more things with this, so that like that's how you can tell if it's gender. And the statistics, I've shown you how to do them. I've tried to talk you through the reasons behind each reason that you do it. But overall, statistics are important because they're typically an unbiased way of comparing, is that different? But then you have to be like, even if it is different, so like look here at the gender, some are significant and some aren't. Those are significant statistically, but is it meaningful? Is it significant, like in a meaningful way? Whereas if I go up here and I look at those guys, female versus male, and I know how small the sample size is, yes, we happen to get a statistically significant result here, but I actually wouldn't really consider that very meaningful. And so I would look at this and be like, I would report that, yeah, on index of difficulty 1 and 4, there was a difference shown. And you would want to then go look at 4 and see, I would do averages and between men and women and see which one was higher. And it looks like men were again higher, but I haven't calculated that. But I would say the difference, and I would say it was significant. But overall, I would debate whether it was significant, and I would go look back at the journal articles. Maybe there's somebody else that shows that females or males are better or more accurate, or anyway. So this is talking, I've asked you questions purely on the movement time. This is not taken into account any of the misses. And I did that particularly because the misses were kind of controlled in the experiments. We said no more than 4, or you had to redo. So it kind of got rid of that aspect. But if you wanted to do an accuracy measure, you'd want to have to define a variable for that. Maybe it was the number of misses. And then you could go do these kind of analysis. Are men or women more accurate? And it could be the number of misses. Instead of this movement time that's faster, then you could be like, which one's more accurate? You could do how many misses. So so there's one of the things about this assignment that I think is challenging is that it was so open-ended. It's here's data, go look at it. I'm showing you these are the first questions I ask myself. Does it fit Fitts' law? Does it go up with the, I did the basic things. Does gender matter? Does age matter? And I've given the reasons behind the statistics, but you can go deeper into it. You can look at accuracy, you can look at speed, you can just always look at data differently, and somebody will report something completely different than another person. I didn't have any of the same data presented to me, even if they were the same topics. I didn't think there was a lacking of thought that went in, but sometimes it wasn't structured. Aims or hypotheses weren't written in a way that described the variables. Like, I think accuracy increases with age. Then you would say, okay, accuracy, you got to define what you're going to say, number of misses and age. Well, the age of the person. You got to make it measurable. You got to make it based off evidence. And then you have to use the statistics, whether it's average or percentage increase, to talk about things. So I asked questions about the we use t-test here. You could use ANOVA, you could use different methods, but we use t-test. Typically, when you're writing an example, okay, let's say 2A versus 2B. If you're writing a sentence to explain that, you would be like, there were no differences between like levels ID levels 2A and 2B, and you can go P equal to 0.59. You go to 2 decimal places unless it's lower than 0.01. And then you need to state, maybe in the next sentence or in your method sections, you would state what test you did. This was performed t-test with two-tailed, it's a two-tailed t-test. T-test, and was this paired? Yeah, and this was a two-tailed paired t-test is what you would say, because the two tails says that factor you put in, and you can, and then with alpha set to 0.05. So that statement there, that performed two-tailed paired t-test, that says the statistics that you ran. You used a t-test. You said that it could go either positive or negative. So that's two-tailed. And you said it was paired because 2A and 2B had all the exact same participants. You also set that, and you said with alpha set to 0.05, that means your significant level was at 5%. So if it randomly happened. So that tells you, in those like 10, 15 words, that tells you exactly what you did. That's your methods part. And over here, there was no difference between ID levels. If there was a difference, you might want to go say, okay, this average was here and this average was here, or percentage, an increase of 5%. That's how I would report it in the results. So those are the kind of things I was looking for. So we'll go here. So basic characteristics of a research hypothesis I've talked about. We go and do a basic literature review about speed accuracy, which I showed you earlier, and you can find 4 highly relevant journal articles. You can probably go read below and see what analysis I make you do and see if make any of them match. Talk about making a decent study design by setting your hypotheses up. Then filling in some of the results, like getting in the basic information, into the descriptive statistics, into the types of results that I showed you there. So it follows pretty exactly along this. And one of the things it does is ask you to make conclusions, though, like discuss why it might not be the best data, or cite it back to your references that you put, which was quite easy, but it does take extra thought, because a lot of the times there was a lot of difficulty in the groups taking the journal articles and relating it back to the results that you reported. Do you have any other questions?
Yeah, so with the actual doing the assignment,
Yeah.
Are we able to print off that page and handwrite it and scan it back, or is it going through the computer, or is it like an exam sort of thing?
I don't know if it, I mean, you could print it off, write it in, scan it back, but it asks for like a figure on one of them. But I guess you could draw it, yeah. So you're probably gonna, I'm asking you pretty much to do this in Excel, because I'm showing you in Excel. I think most people have access. You can write it in, fill it back, but I don't know if I left you enough space per thing. I didn't actually take that into consideration. Best is to probably fill it electronically, but your choice.
Yeah, so it's not like an exam thing where you just kind of sit down and do it, but
No, you can
take time?
take time. Basically, I just want you to go through the steps of an analysis. Think about the variables. I have a question about independent, dependent. Think about, okay, what variables did this look at? How might you analyze it? I mean, somebody might come up here and be like, you should have really looked at accuracy. Right now, I've only looked at the speed part of the speed accuracy, but this is just showing you how I went about doing it. And it'll make you organize the data, which is important. Copying it over is kind of boring, but it's important that you know how to organize it. It's important that you can then go analyze it, do the descriptive statistics first, the basics. That's the basics of any analysis. And then second, are there differences? And that's where you use like the t-test and the linear fit to see if it actually goes together. And that's when you're testing your hypotheses. Yeah, so if you take time, if you have questions, ask me. I'll try to help. This is mainly to try to help you learn concepts, not... I mean, a lot of the points is I feel like this concept was missing, so I wanted to try to help guide the concepts, I guess. Maybe I missed something, so... but let me know. I'm not going to send out this analysis, but you can go back to the video and hopefully... it's quite small text, so I hope people can kind of see what's happening. But, yeah. Do you have any other questions?
Just for you to clear up different things, like with those, the constant, the variant. So the variant I get, you add them all up and divide it, it's kind of the average. But the constant to find it. So is it just taking away like the largest from the plus and the largest from the bottom, or?
It's trying to, it's giving you a directional. Did I miss above or below? So on average, did I miss above or below? And I think a singular constant error makes a lot of sense. +9 on this one, I was really far away, like, especially on mine, like I was plus 1.2 centimeters, like I was really far away. But if you do an average constant variable, it doesn't really tell you anything. An average will say, in general, where is the magnitude higher or lower, but you could also then split that into how many times was I plus and how many times was I minus. Because you might be 10 times on the plus side and 3 times on the minus, but your average could be negative because you were 9, 10, 11 negative and only 1 positive each time. So taking the constant variable, yeah, it gives you the direction, but you have to then be able to interpret. If you take an average of the constant variable, you got to be very careful because of that. Those positives and negatives will cancel each other out. And, but it does give you a sense, are you more often positive or are you more often negative?
So like if you had some scores that was like +8 and you had some that was -8, does that mean the constant error is 0 or 16?
Constant, like, it would be 0. So if you had added up, if you do the average, like, yeah, it'd be 0. But that's why sometimes that added up value, that summarized one, doesn't tell you much. You could then do how many times was I positive, how many times was I negative. That might tell you more in certain circumstances. Or you could break it up and do the average negative and average positive. So you could separate your data so you don't get that mismatch. Like if you get an 8, 9, 10, like a -8, -9, -10, and a +1, 2, and 3, you could just take the +1, 2, 3 and only average that like 2, and you can do the 8, 9, 10 negatives, and you're going to get a -8. So you can see that you're more negative. When you were negative, you were more negative. So it's how you look at it, but it does give you direction, and that's what it's trying to do. And however you decide to summarize that is up to the analyst, but it should make sense with what you're trying to do. And not always is above or below good. Maybe your positive is left and your other's right. You got to make a scale that makes sense for your data.
Like, what if you had, like, going to A again, like, you had 8 above and the lowest you got was 2 above. Is that constant error 8 or is it 6?
Can you go mark it over there?
So with that, the constant error, are you marking from that point or are you marking it from the lowest point? So it could be either 8 or 6.
Oh, you could, I mean, with analyzing stuff, you can define it any way you want, really, but constant error is typically measured from the desired goal. So this would be +2, +8, and if you'd average that, what's halfway between 5? So your average would be a +5. But yeah, so if you have like lots of them up here and only like a couple down here, you're going to be plus, and that tells you, oh, you're on the plus side. So it's trying directional precision. That's kind of what you're going for. Have any other questions?
Yep, one more.
Yep. Good.
How does the variant and the range differ from each other?
Ah, good question. Okay, I'll go back over here. Okay. Let's just... Okay, so let's say we have this data. I'm going to make up numbers here. This is a 1, this is a 3, 3, 5, and a -2. Actually, let's just keep it all positive for fun. And 7, right? So you said range and variance. Okay, so range, they often, it's this what they call the spread in the data, how far apart it is. So it's your minimum value and your maximum value. So it goes from min to max. So min goes from 1 to 7. That's how I would report the range. You could say it's 6. Like if you just want to give the value, what it covers. Okay. So variance is there's different measures of variance. I have to explain this first before I can get to the answer. There's standard deviation, there's confidence intervals, there's different things. But I'm going to talk more about kind of standard deviation. It's one of the basic ways they do it, and it's trying to tell you how. So if you take the mean of this, like what, 1 plus 3 plus 3 plus 5 plus 7, 15, 19, divided by 5, let's just say around 4, right? So approximately 4. So let's say it's 4. That's your average, which I know you know, but that's average or mean, they call it. So then deviation, or the standard deviation, is how far each of your points, your 3, 3, 1, 5, 7, is different from there. So you would basically take 7 minus 4, so you go 3, 5 minus 4 plus 1 plus 4, 3 minus 1 plus 1 plus 4 minus 1. You take the difference of each value from your average, and you add that up, and I think you square it. and then you take the square root, and then I think you divide by the number of samples, so 1, 2, 3, 4, 5. So n. N's a very important number in statistics, so this would be like 5. And that's kind of the math behind it. The point behind it is, so this is your average. It's, on average, how far away are you from your average? And here, your standard deviation is going to be, it's like 1.113. It's going to be a little higher than 1 because of how this works. I think n's in there somewhere. This is probably not the right formula. It's just giving you the idea. It's how far are you away from that average? It gives you an idea. So it's basically going to be something like that. It gives you an idea of where typically somebody landed. It's like, here's my average, and here's where it typically varied. That's why you have those error bars. It gives you like, okay, but then you have here your range, so you get a point down here and a point up here. So you have an average value, a typical landing spot, and then you have kind of the max and min. So this then describes your data quite well. And that's why they often call them descriptive statistics. There's different ways to calculate that, different things you can say. But then if I was going to report this, so let's say this is approximately like 1.1. If I'm going to report how well I just drew those things close to the target, I would say the constant error was 4 plus or minus 1.1, and then I would put range. I'll put this on the next line, and then you can say like with a range of what, 1 to 7. That would be a very explicit way of describing that basic data. So constant error was 4 plus or minus 1.1, range of 1 to 7. And if you were comparing this person to some person that like hit way over here, you could then and say this person was minus 5 on average, plus or minus 2.2, and then you could give a range of -2 to -9. Then you could compare magnitude difference. You can compare, and this shows very clearly that, oh, this person was way more negative. Their circle was bigger. Their range, 7, very similar. But they were just on the negative side with a lot more spread. So it allows you to look at that quite quickly.
That's all my questions.
Okay. Yeah. All right, so I think Vicky might be doing labs